Thanks so much, Helen. And can I say Madame Curie is the absolute best name for a cat ever. I really approve. Okay, I'm just gonna share my screen and get started. Okay, hopefully you can see my slides all right. All right, let's get started. Hello, everyone. Thank you very much for coming to attend this talk today. I'm Abby, as Helen's just introduced. I sometimes feel the need to explain my job role a little bit because quantum developer advocate is sometimes a little bit difficult to wrap your head around if you're not familiar with this kind of role. It's quite it's very unique. Obviously, developer kind of means what it says on the tin. I write code. I come from a software development background. A developer advocate is someone who not only writes code, but also kind of goes out and speaks about that code and advocates for a certain technology in the wider community. And the quantum part is because I specialize in quantum computing. Okay, so without further ado, let's get started on some quantum things. The first thing that I normally like to do when starting a talk on quantum computing is try to give a bit of a tangible example for people to wrap their head around. So let's think of a hypothetical situation. I want to organize a road trip throughout the UK. I know international travel has not been very doable over the last kind of 2 years or so. So I'm sure many of you have been in similar situations trying to think about more local options available. Yeah, so let's think hypothetically, I wanted to visit 14 different cities throughout the UK. If we were going to get our computer to figure out all the different possible routes that we could take, there would be over 3 billion different routes that were doable between these 14 different points. This is actually a relatively kind of simple calculation that your computer could probably, calculate in about a second with a good algorithm. But as you start to make the problem a bit more complicated, the amount of possible routes that you get starts to grow at an exponential rate. So by the time you've added, for example, 22 cities to your travel itinerary, you're now at over 25 million trillion different routes. And at this stage, it would probably take maybe a classical computer, I think the number is maybe like 2,000 years or something ridiculous to be able to calculate iteratively through all those different routes. So as you can see, problems like this, as you start to scale them, our classical computers quickly run out of computing power to be able to compute the outcomes. So as you can see, if you apply this is quite a trivial example here of going on a holiday, but you could easily apply a similar type of problem to something like global supply chain logistics, or even thinking about the way that chemistry molecules interact with each other. These types of problems where with each variable you add, the challenge gets bigger and bigger and the potential outcomes you have drastically increases. This is where you start to see our classical computers struggling to keep up, not having enough memory, not having enough computational power. And this is the type of situation where quantum computers have the most potential to have an impact, because quantum computing essentially represents a new paradigm of computation that utilizes principles of quantum mechanics to perform these kinds of very complex calculations, and they are not subject to the same limitations that classical computers are. They have their own limitations, but in terms of like scaling up these problems, they can potentially provide quite a big advantage. What I will say though is that this isn't some kind of magic new technology that right now is going to kind of revolutionize the world. At the moment, we're still in very heavy research and development phase. You're not going to see quantum computers replacing classical computers anytime soon. And even then, they're probably going to be things that we use more in tandem with our classical computers. But it is a very fast developing area of technology, which is why I find it particularly exciting. There's new developments happening, almost like every week there's a new breakthrough that's happening. And it's just a really exciting time to be getting involved in this space. And I would love to see more women getting involved. So here I am. Okay, so now I've given you like a bit of a more tangible example. I'll just give a quick overview of the kind of key topics I'm going to cover in this talk today. Firstly, I'm going to go through some classical computing basics, because I think in order to understand the key concepts of quantum computing, it's helpful to look at things first in a classical way. Then I'm going to go into quantum computing in a bit more detail. I'm going to try and keep things quite a high level, and some of the concepts might be a little bit difficult to wrap your head around, especially if you haven't come from a quantum physics background. But yeah, I just really encourage you to stick with it. Don't worry if something goes over your head. Some of these concepts can be a little bit out there, and you might need to, look into some of the concepts in more detail in your own time, but that's all okay, as long as you kind of just relax and enjoy. And then once we've kind of gotten through the murky waters of the quantum mechanics realm, we'll get to the good stuff, which is diving into some quantum coding. I'm going to give a bit of a demo of how to use the IBM Quantum Experience platform to start kind of building and running your own quantum code. Then we're going to go into quantum open source. Spoiler alert, Qiskit and the IBM Quantum SDK is all open source. So you can start contributing code straight away to help build quantum computers. And there's also ways you can contribute beyond code to the general community. And then finally, I'll just mention a few useful resources for further learning. And then finally, questions. Yeah, you also feel free to drop questions in the chat as well, or keep them to the end. We're going to cover a lot of content. I'm going to do my best to explain it as best I can, but please do save some questions for the end if there's anything you would like explained in more detail. Okay, so firstly, let's talk about classical computing. So I know, as us software developers, we sometimes will be writing code a lot, but we don't necessarily know what's actually happening under the hood, like really close down to the hardware. But possibly you have some vague notion that computers run on binary, they run on bits, classical bits, which encode information onto the computers. Bits can either have a value of 0 or a value of 1. You can think of that as yes, no, on, off, true, false. And the way that we kind of do all the wonderful things that we can do with classical computers, at the end of the day, it all kind of boils down to a lot of strings of zeros and ones. So if we take one bit with a value of 0, this is equivalent to the number 0 or the value of false. If we take a bit with the value of 1, that is equivalent to the number 1 or a value of true. And then if we want to start building up more complicated numbers or information, we have to start adding more bits to our bit string. So the bit string 10 represents the number 2. And you can see as you kind of go on to more bits, you can start representing more bigger numbers, more complicated kind of programs and equations. And that's where we get terms like, you've probably heard of, measuring the, computational power of a device in terms of like bytes, kilobytes, gigabytes, which are all just representations of the number of zeros and ones basically that make that make that device work. And there's also these concepts of logic gates, which you may or may not be familiar with, which are basically operations that we can run on bits to kind of change the values, manipulate them, and do certain things. This is just a few examples. In the bottom right here, we have a NOT gate. For example, with this, you can imagine this line representing a single bit. If your input bit is a 0, the NOT gate will kind of flip it from a 0 to a 1 or a 1 to a 0. And yeah, so that's an example of one type of logic gate. And as you start to build up lots of more complicated programs or algorithms, at the end of the day, they kind of all distill down to like series of logics, gates, operations on bits. So you get some kind of like a complicated circuit diagram, a bit like that, representing kind of what's going on in your computer. And you can kind of imagine like your any classical algorithm that you're writing in your code at the end of the day kind of ends up looking something like this. And the reason that I'm going into all this detail on classical computing is because if I just show you quickly what a quantum computing circuit looks like, you kind of see the similarities. We can represent quantum computing circuits also as kind of these kind of circuit wires with logic gates on top of them. And I'm going to go into a bit more detail on that. Okay, so quantum computing. I am going to give you a really kind of high level overview of 3 of the core kind of quantum concepts that are useful for you to understand in order to kind of grasp how quantum computing kind of differs from classical computing. The first concept I'm going to go through is superposition, because this is really the defining principle of what makes quantum computing different to classical computing. If we think about our classical computers with our classical bits, essentially they're just electrical impulses, switches that we turn on and off, and information is encoded in those bits. When we move into the realm of quantum, we instead have quantum bits or qubits. And what these are, again, it kind of depends on the hardware you use specifically, but you can think of them as essentially subatomic particles, photons, electrons, really, really, really small particles that is encoding information on our quantum computer. And qubits, as they're subatomic particles, when we get down to that really, really tiny scale, normal physics doesn't really work anymore. It breaks down and we enter this realm of quantum physics where things just work differently. And one of the key aspects of this is the concept of superposition. If we have a qubit that starts, we can have it start in a state of 0 or 1, similar to a classical bit. But then when we put it into a superposition, what that means is now this qubit can operate in any space 1, 0, 1, or anywhere kind of in between. Mathematically, what this means is it's actually a linear combination of 0 and 1. You can kind of think of it as almost like kind of a wave of probability. A really common analogy, which I personally find really useful in thinking about this, because one of the most difficult concepts to kind of wrap your head around, especially if you're not coming from a quantum background, is you can think of it almost like a coin flip. When you have your coin in the palm of your hand, that coin has a definite state of heads or tails. But when you flip that coin and it starts spinning through the air, suddenly, well, is it heads? Is it tails? Well, it's kind of neither, but maybe both. I don't know. It's in this kind of superposition state of both heads and tails. Schrodinger's cat is another kind of principle that another analogy that's kind of used to represent this principle of superposition. When the cat is in the box and the box is closed and we can't see it, the cat is kind of neither alive nor dead, but in the superposition state of alive and dead. So this little diagram in the top left is is similar to those logic gates that I showed you earlier in classical computing, but this logic gate is how we would represent what's called a Hadamard gate in quantum computing. And this is probably the most important logic gate in quantum computing, to be honest, because it's the gate that will turn your qubit, put a qubit into its superposition. So it's important. Remember it, you'll need it for the demo later. And so once we have our qubits in this superposition state, to get any useful information from it, we have to measure it. If you think about that coin example again, when that coin is spinning through the air, we can't really get much information from it at that stage. We have to wait for it to fall back down to the ground, and it will kind of resolve itself into definitely heads or tails. And if we think of that analogy back with our qubit, in order for us to get that useful information, we have to measure this qubit. And the act of us measuring that qubit forces the quantum state to what's called collapse, and collapse down into 0 or a 1 again. And this is a completely random process. We'll get, let's say we take a qubit and we just put it into a superposition and then we measure it. We're gonna get a 0 outcome with a certain probability, and then a 1 outcome with another probability. And because this process is random, we normally have to repeat the measurement multiple times so that we can get a distribution of the possible outcomes. And then we can store that data, that measurement outcome. We normally store it in a classical bit because classical bits are what our classical computers use. And once we have that information encoded again in classical bits, then we can do more classical methods on it, which kind of shows how you can easily plug a quantum computer into our classical infrastructure and use them really effectively in tandem. And again, on the top left, we have a visual representation of what it looks like a measure gate would look like in a quantum circuit. Okay, so the next key principle I'm going to talk to you about is interference. So once we have our qubits in this superposition, there are a bunch of things we can do to manipulate them and special properties that we can take advantage of. Because if we just put all our qubits in superposition and then measure them straight away, we'll just get a random output of like 50% 0, 50% 1, and that's not really very useful. But what we can do is actually use the concept of interference, which is a common physics principle where if you imagine you can use waves to conceptualize it. If you have wave A that has a certain amplitude, so a certain kind of height of the oscillations, and you have B with an exactly opposite amplitude, when you add A and B together, those equal but opposite amplitudes kind of cancel each other out. So if we apply this concept to quantum computing, we can use interference to manipulate our qubits when they're in that superposition. So normally if, say, we just had a single qubit and we put it into superposition and we measured it 100 times, 50 times the outcome would be 0, 50 times the outcome would be 1. But if we interfere, then we can kind of push the probabilities more towards one or the other, that according to what we want. And the way that we quote unquote interfere with the qubits is by doing operations on them when they're in this superposition state. So we can decide to add rotation angles, different types of logic gates onto them depending on what we want to do. Right, next concept is one called entanglement. I know I'm going really fast through everything, so I hope you're all staying on top of it. And yeah, please feel free to ask questions and things as we go along, and we'll have more time at the end as well. So entanglement is the last kind of quantum mechanics concept that I'm going to take you through. Entanglement involves multiple qubits. And again, once our qubits are in superposition, if we entangle them, then they become a single quantum system. If we have two different qubits and we entangle one to the other, they form one quantum system. And that means that by doing one thing to one of those qubits will automatically affect the other. And this holds true no matter how far away these qubits are from each other. So, you know, I could have a qubit with me here on Earth. I could entangle that qubit to another qubit. I could give that second qubit to Helen, and then I could send Helen to, I don't know, the other side of the galaxy. But then if I did something to my qubit, then instantaneously Helen's qubit would be affected by it. And this changes faster than the speed of light. It's instantaneous change over it doesn't matter how much distance. And that's why Einstein called this concept spooky action at a distance, because it really is quite spooky. And it really makes you kind of question the nature of the universe and, you know, what is cause and effect and all that kind of thing. Okay. And coming back to this kind of circuit diagram, hopefully some of these symbols are kind of put into a bit more context for you now. Each of the lines represents your qubit. And you can think of the same way you could think of that logic gate diagram for classical computers as, you know, a representation of what an algorithm looks like. You can think of a quantum circuit like this as a representation of what a quantum circuit, of what a quantum algorithm is. And quantum computing algorithms generally all work on a similar kind of recipe of you put your qubits into superposition, you do operations or rotations on those qubits, you entangle them, you do different rotations, etc. And then you measure what the outcomes are going to be. So each box on this diagram, for example, represents a different operation on those qubits. And then depending on the type of operations and rotations that you're using, this will influence the outcome of your quantum circuit when you measure them. So you can, by doing more complex rotations and manipulations, you can, you know, manipulate the probabilities of what your outcome is going to be. So you're taking something that, you know, would be a random process and you're giving it a deterministic outcome, which is really quite a sophisticated and impressive thing to be able to do. And one of the reasons it's such a exciting area of research, and it's quite it's a massive challenge, and yeah, really exciting. I'm getting a bit nerdy about it now. Okay, so now that your brains are probably all kind of turned to mush, we can move into quantum coding. But before I do, now might be a good time to pause for some questions. I haven't been able to monitor the chat or anything, but does anyone have any kind of burning questions that they would like to that they would like to kind of ask now, or if not, we can wait for the end. I know that we went through quite a lot there, so yeah. No? Okay. All right, great. I've all stunned you into silence. That's fine. There's more time for questions at the end. And
sorry to interrupt you.
Oh, hello. Sorry, could you say that again?
Yeah, sorry to interrupt you. So can we imagine entanglement as combination of different gates in classical computing? Can that be imagined like that?
So entanglement, maybe I should have highlighted this actually. So the gate diagram over here, thank you. I actually forgot to mention this. This gate combination here that I've shown is the simplest way to create entanglement between two qubits using quantum gates. And the demo that I'm going to show you, we're going to create this state actually, which is the minimum entanglement state that you can create.
Okay. Okay, sure.
Okay,
Yeah.
great. Okay, let's move on to the demo that I'm going to do today. So the quantum state that I'm going to walk you folks through is called the Bell state. And as I said, this is the with 2 qubits, the minimal entangled state that you can create. We're going to create a quantum circuit with 2 qubits and 2 classical bits. We're going to put one of those qubits into superposition, and then we're going to entangle it to a second qubit. So if you think about, if we have 2 qubits and say we just put them both into superposition and then we decided to measure them, we would get a completely random outcome of 4 different possible outcomes. We could get 0, 0, 0, 1, 1, 0, or 1, 1. Again, if you want to think about it with the coin flip analogy, if you have 2 people flipping coins completely independently, those coins don't have any impact on each other. So you would get either both have heads, both have tails, one person has heads, the other person has tails, one person has tails, the other person has heads. So 4 distinct different outcomes. But by us entangling the 2 qubits together, we can manipulate the qubits to only give us 2 possible outcomes, either 0, 0 or 1, 1. To give you a bit of a reminder of the quantum gates we're going to use, the first gate we're going to use is the Hadamard gate. This is the one that's going to put our first qubit into that superposition. And then we're going to use this gate called a controlled NOT gate, which facilitates the entanglement to the second qubit. The way that a C-NOT gate works is the full name is a controlled NOT gate. You have a control qubit and a target qubit. In this diagram here, the qubit A is going to be the control qubit, and qubit B is going to be the target qubit. So this means that A kind of controls B. So if qubit A is in a quantum state of 1, then it will force qubit B to flip its sign. But if qubit A is in a state of 0, then it won't flip B. So this means that assuming we start both qubits off at 0, we put A into a superposition. If A then becomes a 1, then B will also be a 1. And if A stays at 0, then B will also stay at 0. So that's how we're narrowing our options down to either 0, 0 or 1, 1. Okay, I'll show you guys, oh, hold on. The platform I'm going to use to show you how to do this, you can also follow along with me on your own laptop if you would like. I might go a little bit fast, so don't worry if you don't keep up. But if you go to quantum-computing.com, you will be taken to this lovely website, which is called the IBM Quantum Experience. I think you can do a kind of single sign-on with your kind of Google Gmail account if you have it or whatever. But basically, once you're in here, there are two different areas that you have access to that I'm going to show you today. One is the Quantum Composer and one is the Quantum Lab. The Quantum Composer is a really nice kind of visual interactive tool that you can use if you don't want to go straight into the code. I think particularly if you're coming from like a research background, maybe coding isn't your thing, but you still understand the concept of circuits. So this is quite useful. So here you can see we have each line represents our qubits. So we have 2 qubits, 0 and 1. You can see here what the probabilities of our outcomes would be if we were to hypothetically measure it. You can see some values about state vectors and things like that, but I wouldn't worry too much about them at the moment. That's getting more into the nitty-gritty on the maths and the physics. And so to create our Bell state, we're just going to very simply add a Hadamard gate to qubit 0, and then we're going to add our C-NOT gate controlling on qubit 0 and then targeting qubit 1. So now you can see down here at the bottom with our probabilities, we would have, of these 4 options, only 0, 0 and 1, 1 are the outcomes that we are able to get. I think for this view, you don't need to measure it specifically because it's just the visual tool, but if you wanted to add a measure, you could add a measure if you want. And then it shows you the outcome of what it would be like if you actually measured it one time and they decided that the one time the output is a 0, 0, 0. But then if you probably ran it like 100 times, then you would get kind of like 50% probability of this one and a 50% probability of this one. Okay, so that's like a really quick intro to the IBM Quantum Composer. And now I'm going to show you the lab. And this is basically in your browser Jupyter Lab instance where we can actually start writing some quantum code. And I'm really excited to get you all started with that. The first thing that I've done here is I've just imported some of the various Qiskit packages. You can also do this locally if you're quite familiar with your kind of Python environments and you want to install it. You can do that as well. Just it's nice to show it in this online environment. The first thing I'm going to do is I am going to instantiate a quantum register, which is going to have 2 qubits, and I'm just going to name it qubit, give it a label as qubit so we can see it nicely. And I'm also going to create a classical register as well, because we need some classical bits to store the results of our circuit at the end. So I'm going to create classical register with 2 classical bits, and I'm just going to call them classical. Once we have some quantum bits and some classical bits, now I'm going to put them together into a circuit. I'm just going to call that QC. Okay. And I'm going to add the quantum bits, the qubits, and the classical bits like that. And then I'm going to, I like to visually see what my circuit looks like. So I'm going to call the draw function. And I'm going to make the output as a matplotlib output because, well, it's just prettier and I like it when it's pretty. Okay, so if I hit Shift Enter, we should be able to see. And of course, I have a typo. There we go. So here we go. Here's our quantum circuit so far. Literally, it's just 2 qubits and 2 classical bits. Sometimes you'll see them kind of combine the classical bits like this into one kind of joint line. But if we want, I can change that output to false if I want. And then we can split it out if you want. Yeah, that's just a convention that you'll see some circuit drawers will do to kind of save space. Okay, so the next thing that we want to do is add that Hadamard gate to the first qubit to put it into a superposition. The easiest way to do this is we have our quantum circuit, and I'm just going to do, add a gate by calling .h. And the argument that I'm going to pass is going to be the position. I need to specify which qubit I want to add that Hadamard gate to. So one way to do that is to call the qubits list and specify which item in that list. You can think of qubits, the quantum register that we created, as a typical Python list, and with the qubit 0 occupying the first item, and then qubit 1 operating the second item in that list. You don't have to specify it this way. If you wanted to, you could just do 0, but I sometimes, when you start building circuits with more and more qubits, it sometimes becomes easier to be really explicit with how you specify it. And well, again, I might just draw it for us. Yeah, and as you can see, this is how we've created a circuit, and we've added a Hadamard gate. So again, using like relatively simple syntax that you might vaguely familiar with already from Python. Next up, we're going to add that controlled NOT gate between the first qubit and the second qubit. So to do that, again, a similar format. We call QC our quantum circuit, and this time we're going to call CX. CX is like a shorthand way of saying a C naught, because an X gate is also is what you would term if you just wanted to flip it. So a CX is kind of a controlled X on 2 qubits. And so this time we need to specify not just the qubit that we want to add the control to, but also the one we want to add the target to. So again, I can reference it the same way as I did with the H gate, qubits. So I'm going to control on the first qubit and then target the second qubit. And we draw it again, and voila, there we go. We've added a controlled NOT gate controlling on the first qubit and targeting the second qubit. For the record, I could do exactly the same thing, but instead of having this specifying explicitly the qubits list that I wanted to, I could just say like 0, 1, and it would give me, oh, sorry. It stored what I was doing previously to my circuit. So now I have to go back to the beginning and retry it. There we go. Yeah, so there you go, same thing, but just with 0 and 1 instead of referencing the qubit register specifically. Okay, and now in order for us to actually get some outputs from this, we do have to add a measure gate. So to do that, we again just call QC, and then this time we add .measure. And we want to specify this time the first argument that we pass is the qubits that we want to measure, and then the classical bits we want to have the output stored in. And you know the drill, draw it again so we can see what we're doing. And I have another typo, of course. I'd be a much better programmer if I could spell. Sorry. This is the thing, it will repeat the commands if I don't redo it from scratch. And now I've missed out the H gate. Live demos, eh? There we go, that's the one I missed. Normally I would probably do some, write some better Python and store these in different variables, but yeah, I didn't do that today. Okay, so now that we have our circuit with our gates, in order to actually essentially run this circuit and get the outputs, we need to get a backend to essentially run this circuit on. You can use a real IBM Quantum computer to do this. Though for this example today, because it's quite a simple circuit, I'm just going to use a simulator because it takes a lot less time to run the experiments, and sometimes it can take a bit of time to load. So in order to the Qiskit package that you can use to simulate quantum circuits is called AIR. And AIR has a lot of different backends that you can use to run circuits on. So if I call air.backends, it prints out a list of all the different simulators that you can use. You don't need to worry about too many of these things at the moment, unless you're kind of really into quantum physics. It might not mean very much to you, but basically it just allows you to do all sorts of different things with the measuring of your quantum circuit. We're just going to stick with the default one, the AIR simulator. So to access the simulator, what we're going to do is we're just going to create a variable called simulator. I'm going to call air.get backend, and we're just going to call the AIR simulator. This is just the default one. And then what we have to do is we have to transpile our circuit. So what this means is we have to convert our circuit into something that is understandable for the actual backend to use. It maybe doesn't make much sense, I guess, if it's a simulator, but they try to have the simulators and emulate what the real behavior would be like as much as possible. So we're going to call transpile the quantum circuit for this simulator. And then once we do that, we'll be able to get sorry, one second. I think just need to double check I have the right code here. Yeah. I always forget this, but you have to make sure that you run it with a certain number of shots. And then call result to get the results that you want. So yeah, so you essentially, you have your simulator, you run your circuit on that simulator, and then you get the results and you store it in a result. You can store it in a variable called result here. I'm setting shots as 1024. It doesn't particularly matter. We just want a really high number to be able to, you know, get as many outcomes and get a good distribution of results. Okay, so if I run, and then once we have the number of results, we want to count how many results we get for each outcome, 0, 0, or 1, 1. So we're going to call count, going to create a variable called counts, and then we're going to say result.get counts for our circuit that we just transpiled. Okay, so in the background, our simulator should have done all of its quantum stuff and calculated some results for us. So if we print what our result will be, we should get this very long kind of object, which maybe does not look like much to you, but if we print what the actual counts were that we got from this result, then we'll get something a bit more readable, which is, as you can see, we got roughly a 50-50 split between outcomes of 0, 0 and of 1, 1. You can also make a nice little histogram out of it if you want. If I can remember how to do the syntax, counts, title, my cool circuit, whatever you want. And then, yeah, you can see this is quite similar to what was shown in the Quantum Composer itself, the 50-50 split between these two outcomes. Sorry, my computer's in dark mode, so you don't see the axes very well, but yeah, there you go. And that was that's just a little demo for you for how to create your first quantum circuit using the IBM Quantum Experience. There are a ton of resources that you can find online to help you do more of this, do more of the Bell state, do more complicated states and things like that. I'm running kind of short on time, but I am going to move on now and start and give you a really quick run through on all of the quantum open source things that are available that you can, if you're a big open source fan, then definitely you should get involved in all the different things we have going on. I'm going to give you a bit of an overview of all the different repositories that we have, maybe just highlight a few of them and where the code lives for the different parts of the Qiskit ecosystem. So for those of you familiar with GitHub, we have 3 different GitHub organizations where the majority of the code lives for Qiskit. We have Qiskit, Qiskit Community, and Kiskit Partners. Qiskit itself is where the main code for running code on quantum computers lives. There are a lot of repos there, and I really recommend going and diving in yourself and having an explore. I'll just highlight a few. Almost all of them are based on Python, but there are a few others for people that have different language backgrounds. Whatever you're interested in, there's probably be able to find something. Qiskit Terra is the kind of the core repo for the quantum computing code. That's where the real meat of the code base lives. Then there's also a few really interesting newer repositories that we kind of group together and call Qiskit applications. And this is where you can start seeing how code is starting to be developed to help kind of find real world applications for quantum computing. So whether it's in machine learning or Qiskit Nature is for chemistry applications, there's Qiskit optimization, Qiskit finance. Qiskit Air was the package that I just briefly showed you, where you can get the different backends, different simulators to simulate outcomes for quantum computers. This is written in C++, so any C++ developers out there, go check it out. And then even if you're a web dev and you like JavaScript, there's even repos for you. We have Qiskit.org as the main website that we have for kind of talking about Qiskit and Qiskit software, and that's all also all open source, and it uses the Vue JavaScript framework. And it's all open source. So go wild, go explore. We also have Qiskit Community Organization, which is where more of the kind of community focused repos live. We have a textbook to help people get started in quantum computing, and the code for that is all open source. Qiskit translations, if we really try to make our documentation as accessible as possible to people all over the world. And the best way that we've been able to do this is by getting people who speak multiple languages to help us out with translating our documentation. So if you speak another language, please go and help us out there. And we finally also have a feedback repo modeled on the GitHub and NPM feedback repos, where you can join in discussions on the development of the Qiskit software, hear about our demo days and our development meetings and things like that. And then finally, the last organization is probably the smallest. It's called Kiskit Partners. This is for people that are really interested in the different backend providers that you can plug into Qiskit. So you can have, like, Qiskit IBM is the main IBM provider backend that links Qiskit, the software package, to the real hardware in the backend. Qiskit IonQ is, for example, IonQ is a different type of hardware that you can also plug Qiskit into using the Qiskit IonQ provider. And Qiskit Runtime is a new service provided by IBM, which kind of, again, without wanting to go into too much detail, it essentially makes it quicker and simpler to do conditional programming on quantum computers. And it's kind of a big new feature that's been released this year. And it's all open source, which is fantastic. There are lots of different ways for you to contribute. You can find a bug and open an issue, or even better, you know, open a PR for that issue. You can look through existing issues in any of these repos. Some of them have good first issue or good for community tags. So you can find stuff that are maybe better for your first, you know, your first PRs and things. You could also just kind of comment and review other people's work, add to discussions, attend development meetings, or even just create your own project using Qiskit. I think this is the last slide I'll probably have time for, but I think it's really important, so I wanted to mention it really quickly. And that's just a little thing on open source etiquette. For those of you who maybe are already familiar with open source, I'm sure you all know this already, but I think it's always good to mention it again. We have a few kind of housekeeping rules that we like for people who want to get involved with Qiskit in an open source capacity. And that's please, please, please read the code of conduct and the contributing guidelines. Also check if PRs and issues already exist before you open new ones. Ask to be assigned to issues before starting work on it. Please remember to be patient. The maintainers are very busy people, and especially outside of normal working hours, they might not be very quick to respond. Of course, be kind and empathetic to your fellow you know, open source contributor. There's always a person on the other end of, you know, whatever GitHub comment you're making. And finally, don't be shy. We are all a really fun bunch of nerds. I promise we to the Qiskit SDK. And I know it can be a bit scary sometimes to kind of start talking and working with people who seem to be working in another quantum realm with all their crazy quantum knowledge. But yeah, we really welcome anyone to come and join us. Okay, I've already gone a bit over time. So I think I'll stop there and just open up for questions. Who would, yeah, is there stuff happening in the chat? Does anyone feel like they'd like to volunteer to ask a question? Now is your moment.
I have a question. Can you hear me?
Yes, yeah, please go ahead.
So the program, obviously the demo program, I really enjoyed the talk, by the way, very nice. And the program that you showed obviously was a very simple example to just kind of get the basics across. What would a program look like that actually solved an interesting problem like the traveling salesperson problem you showed? I mean, like how big and kind of, can you give any estimate of like how complicated it would look?
Yeah, that's quite a difficult question to ask because I guess it depends how you define complexity. But there is, you can have, they can get very complicated in terms of the number of qubits that you need to run a certain problem, the number of gates you have, what type of gates. The gate, I really only showed you 2 gates, but there are lots of different ones, and you can get really sophisticated in how you even calibrate them with different rotation angles and things like that. I guess there are a lot of people that dedicate a lot of time to researching the best way to create quantum algorithms. And they obviously strive to make them as simple as possible, because the more complicated and the more gates you start adding, the more qubits you start adding, the less feasible it is to actually be able to run your run your quantum circuit. I didn't really touch on it much in this talk, but I did mention that quantum computers themselves have some big limitations, at least in the near term, because with the number of, as you increase the number of qubits that you have, and as you also increase how long it takes your circuit to run, the accuracy of your results decreases quite dramatically, because I mean, like I said, you're dealing with subatomic particles, you know, like they are so sensitive, you know, a minor change in temperature, or, you know, all these tiny little things, a light breeze could completely kind of mess up your qubit and make it lose its quantum state. So there's a big incentive for quantum algorithm developers to make their circuits as simple as possible. But yeah, we're starting to get, you know, the hardware is becoming increasingly, you know, sophisticated, and building the numbers of qubits to like the 50s and hundreds of qubits. So as you can imagine, then the complexity of the circuits you're able to perform also increases. Yeah, I recommend like Googling some of them, and you'll get kind of maybe a visual representation of some of the more complicated ones.
Thank you. I have a second question, but I want to give other people a chance, so I'll pause.
Sure. So I'm also looking in the chat. I've been a bit slow with catching up. I'm not good at speaking and writing code and looking at the chat at the same time. But I'm looking through them now. What does the computer look like on the outside and the inside? What are the components? Oh, I like this question. They look very cool. Maybe I can just quickly Google a quantum computer for you. This was a mistake on my part. I should have included a picture of what a quantum computer actually looks like. But they basically look like these massive big refrigerators from the outside, and then on the inside you have a lot of wires, and you kind of have this almost golden chandelier thing on the inside. Yeah, here we go. So this is what it would kind of look like on the inside, with all these different wires, but this isn't really what you would see. Normally it's encased in this kind of protective covering, which keeps it very stable.
Your screen. Sorry,
oh no, I'm so sorry.
Your screen.
I'm so sorry. hold on. Okay. You'd think after 2 years of a pandemic, I would, you know, not fall prey to this kind of sharing screen mishaps. But yeah, this is what they look like. This kind of chandelier type thing is what it looks like on the inside with all the wires, but normally it's coated in this big kind of refrigerator sleeve. And I am not a hardware person, so please don't ask me how this stuff actually works. But you have essentially like a quantum chip that looks like this when you zoom in. And I think each of these little things here is the actual qubit, and then these kind of pipes leading into it kind of send microwave pulses through to kind of, a quantum gate really is just a pulse, a microwave pulse that you send to the qubit. Yeah. Does that answer your question? Not sure who put it in the chat, but I hope it does. Okay, let me see if there is. Does anyone else have any questions they would like to call out loud while I look through some of the written ones? Nope. Someone in the chat asked, is it easier if the shots parameter is a power of 2, or is that arbitrary? I think yeah, I think it's pretty much arbitrary, to be honest. The bigger the number, the better. Yeah, for that kind of small scale circuit that we're doing. I'm actually not sure, depending on, there might be some differences depending on the exact specifics of the circuit that you're doing. But yeah. Okay, cool. Any other questions from anyone? What is qubit nature? Qiskit nature. Qiskit nature is the Qiskit package that is designed for, it aims to simulate molecules using quantum computers. So, and this is an area that I find particularly exciting. Molecules are one of those, molecules is one of those really computationally hard problems, because there's just a lot of different variables that go into trying to like simulate how things work on a molecular level. And simulating molecules classically is very difficult, and we don't do it very effectively. So this is one of the really exciting areas where quantum computing has the potential to provide an advantage. So Qiskit Nature is the GitHub repository where there is a lot of research going into into that side of things. Do you anticipate this generation of programs being written by ML algorithms, like a kind of high-level compiler where you specify the goal symbolically and software generates the quantum program? This is really interesting because actually just the other week, a colleague of mine tested out GitHub Copilot with our Qiskit code. And for those of you that don't know, Copilot was released this year by GitHub, and basically it takes all open source projects on GitHub and uses that to feed its ML kind of service called Copilot that will basically like natural language processing, but for writing code. So you can write, I don't know, make an API call or something like that, and it will print out the code for you based on massive data sets from any open source code that's on GitHub. And so one of my colleagues thought, well, all of Qiskit in quantum computing code is open source, so maybe it can work with quantum code, and it does actually. If you use GitHub Copilot or the equivalent library that it's based on, and say, I want, write a quantum program, it will write a program for you using Qiskit. Yeah. So yeah, kind of. I mean, I don't know if I envision a world where, everyone will be writing quantum. You'll have an ML algorithm writing quantum code for you, but just in the same way that I don't predict Copilot would, completely take over the role of all software developers. So yeah. Okay. Anything else from anyone? I'm gonna stop sharing my screen so I can look at you all. Okay, well, if there's nothing else from anyone, I guess I'll hand back to Helen then. And thank you all so much for being part of this talk and sticking with it through all of the pretty intense subject matter.
Thank you very much, Abby. That has been a great presentation. I can't wait to go and try Qiskit.